Hey, welcome everyone for the discussion session today. So we dive into questions on asymptotic safety and GR with non-metricity. We will start with some remaining questions during the talks. So first we have a question from I think here. Yes.
Well, good morning, and my question will be the following. If we consider non-metricity gravity, first, can we treat this non-metricity gravity as a particular case of metric affine gravity, which is more generic? Second, whether we can couple it to other fields, because if we deal with usual metric affine gravity and impose some restriction, we can couple up to the bumblebee field, thus allowing for Lorentz symmetry breaking. And if we have purely non-metricity gravity presented by you, can we do the same thing?
Yes, thank you for the question. Yes, I mean, in this case, we have also metric affine gravity theory. It's just now we have the specificity that we also imposing torsion to be completely zero. But you could also have a generic geometrical setup where you have both torsion and non-metricity. And in this way, you could also represent gravity basically in terms of both torsion and non-metricity, and you have a general equivalent theory of gravity. And now concerning whether or not you are willing to break symmetries or whether or not you are willing to allow some additional couplings to certain fields, this of course depends on what you are willing to do. If you are allowing, for example, non-minimal coupling to the hypermomentum, or if you are following the minimal coupling principle. So your scenario, you could also do that in terms of non-metricity. You just have to impose further that torsion vanishes. And then you could allow in the hypermomentum, for example, an additional scalar field that couples to non-metricity if you wished.
Hi, Lavinia. It's Kelly Estelle here. I don't have a question so much as a comment. I've also been interested in these various reformulations of general relativity in different clothes. Another one basically flows from the way mathematicians talk about manifolds with torsion, as in Kobayashi and Nomizu, the notion of development, which can be implemented in a reformulation of one should use first of all the Vierbein formalism, so that you're actually ready to couple to fermions if you want to invite them into the game. But so you have Vierbeins and connections, and you can rewrite general relativity as a gauge theory, really as a gauge theory of now choose your group depending on what you want for your cosmological constant, either de Sitter or anti-de Sitter or ISO 331. And it really is a gauge theory of that. It's a generalization, it's an extension or development of Kibble and Utiyama, but to actually write theories that they're fully invariant under the full group. But what I wanted to say is then now a characteristic of Einstein's theory comes up in this language, which you otherwise don't see. In order to do that, this larger group, versions of SO5, right, as you say, has to be spontaneously broken in four-dimensional spacetime, as opposed to three-dimensional spacetime, where you have a Chern-Simons type action where it's not spontaneously broken, as Paul Townsend and Anna Achukaro found. And so we built field equations and an action and so forth. And basically, you have to extend the tangent space to an affine tangent space, where as you wander around in space-time, you first of all, you start on a journey, you drop a penny somewhere on your space-time, and you go wandering around, and you keep track both of the orientation of your vectors and also translation. So you make a little map where you keep your vectors rotation, and you also write where you think you are on your map. And when you come back to your penny on space-time, you see what your map looks like, and you see your vectors are twisted, and your map is not closed. So that's curvature and torsion right there. And but in order to actually make Einstein gravity, you have to then introduce another field, which is the implementation of spontaneous symmetry breaking. So there has to be a Goldstone field in the field, which allows you to tie up all the indices without actually introducing a metric. So there's no metric there. But then you can do it. Okay. So, but it's this instance of spontaneous symmetry breaking, which seems to characterize Einstein gravity in 4 dimensions. I don't know. And there are other things you can try to imagine playing with in this formalism. I haven't tried to quantize it, but it's just another way of looking at Einstein's theory in a different language, and you see maybe somewhat hidden structural features that you otherwise might not have noticed. And I suppose you can also come up with perspectives like that from your non-metricity formulation. I would say basically, in order to introduce fermions, I don't really see any good way other than actually reformulating what you're doing in terms of Fierbeins. You need to have the local Lorentz group, otherwise you don't know what to do with fermions. But presumably you can redo everything in terms of a Vierbein formulation and have non-Vierbeinicidity, whatever you call it. You have to introduce a whole bunch of new fancy words that I've never heard.
Yes, absolutely. I mean, you could take the formulation that I just represented and write them in terms of the Vierbein formulation. I'm just writing a different way of writing, basically the Lagrangian, without having to choose a Vierbein or a very specific frame or whatever. But the price that I have to pay is that I have to have these Lagrange multipliers that impose that Riemann vanishes and the torsion vanishes. If you wrote in terms of the Vierbein, you could directly impose that at much earlier level, and then your Lagrangian is probably a little bit more simpler or not so convoluted. But if I want to write everything fully covariantly without choosing a very specific frame or Vierbein, then I have to introduce these Lagrange multipliers. And you are absolutely right. I could also do this entirely in terms of my tangent spaces, my Vierbeins, and then I can also say that if I map that back to my spacetime, to my manifold where my fields live, now it depends what I am assuming, what the underlying killing metric is. For example, I guess for phenomenological reason, it would make sense to assume Lorentz SO31 or SO3 in general. But depending on that group that you are choosing, you will end up with a very different theory. So in this sense, you're absolutely right. I mean, the thing that you did allowed just curvature and torsion, but you could go further and allow also, for example, non-metricity.
Questions? I will take the opportunity to ask a question to Lavinia. So I was wondering, any f of q, you mentioned f of q, but I think it should be possible to write any f of q as scalar tensor theory and GR in metric theory. So basically, you can write an equivalent way, in metric theory, the scalar tensor theory, and then we don't need to worry about non-metricity and all. Is it correct?
No, it's not. It's not quite correct, because so you're assuming that because GR is equivalent to the non-metricity formulation, so R is equivalent to Q. Now you try to make the assumption that f of R is equal to f of Q.
No, I'm not making that assumption. So you have f of q and with some degrees of freedom, and then I can write some equivalent theory. Cannot be directly related by any transformation or anything. I can write an equivalent theory which give exactly the same results as f of q.
I would doubt that, because if you have a scalar tensor theory, you have a tensor field plus an additional scalar field. You have in total 3 dynamical degrees of freedom, right? Whereas if you have a f of q theory, in total you have 7 degrees of freedom.
I can
it means
introduce
that,
more degrees of freedom in the metric theories. So what's the problem?
yeah, then you can do that, of course. You can try to find, but basically your question would be, what kind of complicated Lagrangian I have to write in order to be able to write that as a metric theory. And then you will have to introduce additional 5 more degrees of freedom so that you have at the end the 7 degrees that is encountered in f of q.
Yeah, I think that's precisely the question. If it is always possible, or if there are limitations in doing that. So,
I mean, if this Lagrangian is super duper complicated, it could be hard to find it. And then the question is, why would you do it? Because if all they covariantly nicely packed in your Q, why would you then do that?
maybe let me change my question in a different way. So does that non-metric formalism, like f of q, anything, will guide us to think about right scalar tensor theories with some right number of degrees of freedom? Some kind. I mean, it's difficult to guess. If you are in metric theories, if you want to introduce degrees of freedom, there are countlessly many possibilities. Does that understanding of physics from non-metricity or torsion will guide us to think better on writing equivalent metric theories with right degrees of freedom with right number of right terms?
I don't think so. I mean, because the term right already
okay.
ask me a lot more than what I can say. I mean, f of q would be a very specific way of moving away from general relativity, and maybe it's even very hard to write that in terms of metric theory because it's probably super duper complicated. But I don't think that it can then guide us saying that this scalar theory is more interesting or phenomenologically more viable, because, I mean, how could you make this argument based on what?
Mm-hmm. We have a question. Yeah, follow up. Yeah,
just a comment. In terms, this is somewhat similar to writing GR in Palatini formalism, with the connection being independent. And there's an old paper by Peter van Nieuwenhausen and Ergen Sezgin, maybe about 1979 or so, or 1980, where they looked at the general family of quadratic curvature theories in that context, and then in where you find the ghost-free one is hiding differently in the sort of sea of possibilities, but that's somewhat similar to what you're talking about in that it's an old paper where they looked at the general class of quadratic curvature theories. That's not f of curvature, f of connection, but it's it's a piece of it.
Yes. So if you have the Riemann curvature, and you look at all the possible contractions of this Riemann curvature, but now you work in terms of Palatini and not the Christoffel symbols, then you can actually completely, at the level of the Lagrangian or equation of motion, show that there are the typical ghost degrees of freedom that you would naively have in such a quadratic curvature contractions if you wrote that in terms of the Christoffel symbols. And if you didn't have the matter field, then basically the connection wouldn't have any implications. But because you have matter fields and your connection in this quadratic Lagrangian doesn't introduce any dynamics, because there is not such thing as like partial gamma squared. And that would mean that the connection is not a dynamical degree of freedom. You can integrate it out, but once you integrate that out, your matter coupling basically changes. So if you want this general quadratic Riemann curvature contractions a la Palatini, doesn't introduce any additional degrees of freedom and also no ghost degrees of freedom. But the price to pay is that your matter coupling now changes.
Now we have a question online. Jens?
Yeah, hello everyone. It's Jens again. Lavinia, like a follow-up question on your talk regarding the right-hand side of the field equations. So in Einstein gravity, we know that you can only couple to the Einstein-Hilbert energy momentum tensor, and then for example, if you have torsion, you're allowed to couple to spin currents as well. Do you have any extra currents that your gravity model can couple to? For example, like a dilation current that is related to the conformal group, since you mentioned the scaling behavior, you know, of
Yeah. This is the question about the minimal coupling principle, right?
Yes.
So in principle, I could couple to the hypermomentum.
Yeah.
In my basically on the right hand side of my equations of motion, but that would explicitly break my minimal coupling principle. So in the case where I have just standard general relativity, I have basically rewritten the pure gravity sector in terms of this non-metricity interpretation, and then the matter sector follows or has exactly the same minimal Lagrangian that we have in the standard model. And only if you explicitly assume that this matter fields directly coupled to the connection, you will get the hypermomentum. And all this conserved currents, stuff like you say, they are actually hidden in this hypermomentum and the covariant derivative acting on this hypermomentum. But in my case, I didn't allow that this hypermomentum exists. So I didn't allow that this matter fields explicitly couple to the connection.
I see.
I'm following the minimal coupling principle.
Yeah, thank you. Because I was also wondering in connection to Astrid's talk, since Astrid, you're interested in the role of matter, and if you think about possible truncations, do you look into post-Einsteinian types of geometry that have maybe non-standard ways of coupling to gravity? Is that something that plays a role?
So you mean whether there's, for instance, works that would investigate whether like a formulation including non-metricity would be asymptotically safe?
For example, yes, or just a smaller case, you could just say, look at torsion, for example.
Yeah.
Different matter sources, yeah.
I mean, yeah, and I mean, in principle, asymptotic safety is a general framework, right? And you can apply that to any field theory. And so you can, you know, basically write the full list of all the various equivalent formulations of GR and then look at the corresponding theory spaces and ask whether they are asymptotically safe. A little bit in a direction like that has been done, in particular by Martin Reuter with some of his former students, for instance, in settings where you would have an independent connection. And I believe there's also work by Roberto Pacacci with torsion in 3D, I think maybe. So yes, a little bit of exploration in such directions has been done. I would maybe for the moment argue and a lot of that is technically significantly more complicated than just looking at the standard metric formulation. And so for this reason, I would say, well, at the moment, we don't seem to see any indications that the degrees of freedom just in the standard metric formulation are insufficient in order to make the theory asymptotically safe. And so therefore, there isn't any intrinsic need to introduce further sort of non-geometric degrees of freedom. But of course, in principle, it's a very interesting question to also understand, you know, are these theories asymptotically safe? Do they have maybe a different infrared phenomenology and so on? Some of that is technically a bit more challenging to address than calculating in the pure metric framework.
Yeah, because I was wondering, I mean, people usually say in the high energy community, for example, Andy Strometer always says this, that all these non-GR terms, they're usually generated by the RG flow anyway. So the question is then, is that legitimate to not look into these terms, or is that more like a challenge, a computational challenge at this point, or is there any reason to assume that they will not affect the results?
So I think you have to distinguish two things, right? I mean, depending on what you mean by non-GR terms. Any sort of local term that you can build out of the metric, like higher order curvature invariants, they will in general be generated by the flow. And a lot of those are accounted for in the standard calculations. It's a different question, though, when it comes to introducing new degrees of freedom, right? For instance, when you make your connection independent, you're explicitly adding a whole new set of field configurations that you're summing over in the path integral. So it's really a priori choice of configuration space over which you're spanning a path integral. And so that is not something that is automatically generated by the RG flow. So if you pick your original configuration space and you say, I only want to look at different metric configurations and my connection is a derived degree of freedom, not an independent degree of freedom, that gives you a theory space that contains lots of curvature invariants beyond GR, and they will be generated. But there isn't anything that will take you out of this configuration space and tell you that you necessarily have to make the torsion dynamical, or that you have to make the connection independently dynamical, or introduce torsion or non-metricity or anything like that. So that's an a priori choice that you can make.
Yeah. Thank you, Astrid, and also thank you, Lavinia.
We have a question here. Okay, follow up online from Paulo.
Yeah, hi Lavinia. I have a question for you. I don't care about quantization. I'm just worried about classical observable. Can you compute the S matrix? Can you compute the waveform and compare? I mean, these are quantities that you observe at LIGO. What are the difference between this quantity in GR and in your theory?
Okay, now it should work.
Yeah.
Thanks, Paulo. Nice to hear you again. It's a long time that we saw each other. Yes, so in terms of observables, like you mentioned, gravitational waves, or if you really would compute the scattering amplitudes, if you stick just to the general relativity, then you would obtain exactly the same results. So the short proof that I was given in just one line was that the Q scalar is the same as the Einstein-Hilbert Ricci scalar up to these boundary terms. And so if you now compute your Feynman diagrams and at the vertices, if these boundary terms do not contribute explicitly, if you want to basically make comparison to standard GR, then they shouldn't give any differences. But if they contribute explicitly in the vertices, they will probably give rise to differences. So the equivalence is only at the level of the equations of motion, meaning that you have your classical theory, imagine, and now you compute how gravitational waves would propagate, how they would dynamically evolve. You would have exactly the same dynamics and evolution as in standard general relativity. Only in cases where you use the action instead of the equations of motion, there can be differences. For example, as I was mentioning, when you compute the entropy of a black hole, where you use the path integral approach, there is the action, right, that enters explicitly. And then because these two theories differ by boundary terms in the calculation, there could be differences. And I guess the same thing you could argue also for all the Feynman diagrams, the scattering amplitudes. If the difference is due to these boundary terms and they give rise to contributions to the vertices, then there might be differences. But in terms of dynamics, they are the same.
Okay, thank you very much.
Question.
Question for Astrid. So you mentioned this example where you have the flow and you had intermediate fixed points and they made your Wilson coefficients large. So, but I'm a bit confused because, I mean, this is the flow for the dimensionless coefficients, right? But you would still have this, the one that, the scale, the inverse Planck mass. So even though they would numerically be large, they would still be suppressed, right? So in that sense, they would still be, unless they would be like enormously large, right? They would still be unobservable in that sense, right?
Yeah, so yeah, you're right that you can, I mean, you basically have freedom, right? I mean, there's a dimensionful coefficient and you write it as a dimensionless number divided by some scale, so you can always trade between the two. But let's fix the scale to be the Planck scale. And then if you really want the Wilson coefficient to be of order 1, right, then of course the dimensionless coefficient has to be of order 10 to the 38, I guess. So electroweak scale over Planck scale squared. And within this toy model, you can in principle achieve such extremely large numbers if you just choose trajectories that spend more and more time very close to these interacting fixed points. So in that case, because of the vicinity to this interacting fixed point, you're basically just switching off the canonical scaling that usually suppresses this coefficient. There are, of course, two things to keep in mind, right? The first is that all of this is within a toy model, and it's not clear whether there are such, interacting intermediate fixed points in the full, SMEF with the full fermion couplings. That's the first one. And the second is, of course, that you have to choose trajectories which really pass very, very close to these fixed points to really span many, many orders of magnitudes close there. So in some sense, it becomes a somewhat, sort of fine-tuned scenario in that you're not picking one of the very generic trajectories that comes out of the first fixed point, but that you have to tune a little bit. But it nevertheless sort of is an exciting possibility that just shows that, this conventional expectation might not always be true. It really depends on the structure that your RG flow exhibits, what these Wilson coefficients would be. But if you would ask me whether I would expect that this is the situation that is realized, then I would also be skeptical of that. It's just a sort of toy model that shows that there can be interesting structures in the RG flow between the Planck scale and the electroweak scale, even if there is no new physics on these scales.
From Benjamin, follow-up question.
Yeah, just a quick follow-up on that aspect. I was wondering whether it makes sense to define some kind of measure on this potential values of the Wilson coefficient. I mean, kind of implicitly, we assume that all values are equally, likely, if you want, in this kind of landscape. But is that a reasonable expectation, or is it just simply another assumption that we say, okay, like the generic, according to some, I don't know, flat probability distribution, we expect an order 1 coefficient, but then at the boundaries, we are saying, yeah, we are introducing a new scale, basically. Is that not just an additional input in a sense?
I'm not sure whether it's an additional input because, I mean, it's not an input in the sense that it arises out of the structure of the RG flow. But of course, what you're saying in terms of sort of discussing this whole question in terms of probability measures on the space of couplings and how probability measures evolve, and how a flat distribution of a coupling evolves into something that is maybe non-flat and where the boundaries exhibit interesting structure. That's indeed something that is work in progress and hopefully will be out in a few months. I find it a very useful perspective to rephrase many of these statements in precisely this language to say what happens to trajectories generically and what is the probability for something special to happen and so on. So it definitely makes sense to rephrase it in this way. And then you can make statements, for instance, on what is the relative number of trajectories for which such non-standard scaling of Wilson coefficients comes out, and you can try to quantify maybe the degree of specialness of such trajectories and things like that. Does that address your question?
Yes, thank you.
Yeah, question.
Hi, Astrid. It is I again. I wanted to come back to the issue of neutrino masses, and basically the question is relationship between all of this and renormalizability. So I would like to know, is there any question you can ask from and by the way, in asymptotic safety, I don't want to be too prescriptive and say it has to be a non-Gaussian fixed point. Let's just allow that into the discussion as well. What you said about killing off the dimension 5 neutrino mass in the effective theory, of course, that's only part of what you get when you integrate out the in the seesaw mechanism. You develop dimension 5 and dimension 6. So you should go back and re-ask the question where both of them are present. And if you do that, is there any question you can ask such that the answer is exactly the structure that you get from the renormalizable theory after integrating out the heavy mode. Can you find it a common language? Can you ask a question such that the answer is exactly what you get from integrating out the heavy right-handed fermions?
I'm not sure I'm precisely understanding the question. So are you asking, is there a fixed point structure that is induced purely by, gravitational fluctuations that I couple?
No gravity here.
But
I'm just standard. Gravity's too complicated for me.
Oh,
I
so
just was
just
talking in
below
terms of
the
standard
Planck
model.
scale? Mm-hmm.
Yeah.
But then is your question basically about the mapping of functional renormalization group to other formulations of renormalization?
Any technology you want to use is fine.
Mm-hmm.
It's just I'm trying to understand the relationship between asymptotic safety and other. I mean, this is one of the things, Weinberg towards the end of his life was being a bit obscure about what he felt about renormalizability. And he was considering asymptotic safety as a kind of an extension. So I'd like to try to have a better understanding. I have this guy who's secretly gone off and integrated out the fermions and handed you the effective theory, not telling you how he did it, and then over to you with asymptotic safety to study it and various coefficients and so forth. But he didn't tell you the precise numbers. Is there a question you can ask from an asymptotic safety point of view, such that you get exactly the structure that you would get if you realized that you had integrated out the right-handed neutrinos?
So basically, I think maybe if I let me
you
let
have
me
these
repeat
positivity
what I think you're
requirements
saying
and so forth.
back
You
to
have
you,
all
and
sorts
you,
of
you can tell me whether I
guidelines.
understood correctly. So if you're basically trying to understand if I get an asymptotically safe fixed point, is there, for instance, an automatic relation in this case, let's say between the dimension 5 and the dimension 6 operator, that is the same relation that I would get if I had integrated out
exactly
heavy fields? I don't think that will generically be the case. I don't see a reason why.
Not generic. I'd like to have a question such that specific comes out. You probably have to ask a refined question to do it.
Yeah, but so what I'm trying to say is that I would generically expect that the relations that you get between couplings that arise from integrating out heavy modes, that those are different relations than the relations that you get by requiring asymptotic safety. So in that sense, I would expect that if you do calculations with high enough precision that you can really determine these two surfaces in the space of couplings, that you would be able to tell, is this a theory in which somebody has integrated out heavy modes and not told me about this, or is this a theory which is asymptotically safe but doesn't have any heavy modes?
So you think the two procedures diverge? They're actually different approaches with different results. That the ultraviolet complete theory you get from asymptotic safety does not contain the renormalizable one.
Yes, I would in general expect that those are different, and maybe circling back to the result on the Weinberg operator that we have here. I think that's an example, right? Because the asymptotic safety condition is that this operator vanishes. Whereas if I would have had some very heavy fields that I would have integrated out, I mean, like a heavy Higgs, then in general, this would produce a non-vanishing value of the Weinberg operator,
yeah,
right?
Exactly.
So, I'm talking in truncation, of course, right? But this is a simple example where the two requirements could be distinguished. And in that sense, indeed, I would be able to tell that this is, you're handing me the value of that coupling, and I would be able to tell you this is a theory that is compatible with the asymptotic safety condition, but not the one with heavy new degrees of freedom. And so in that sense, I would say it's really physically a difference between demanding a perturbatively renormalizable theory where you have a Gaussian fixed point at the end and you're integrating out some degrees of freedom, that is physically different from demanding asymptotic safety above some mass scale. And it generates different relations between the couplings. That would be my general expectations. But of course, it would be very interesting if there was a theory where these relations would exactly agree. But I would be quite surprised if that would happen.
I think the people at Fermilab would be unhappy with you because they really want that dimension 5 operator.
I mean, it will be generated in principle if you have, asymptotic safety with the seesaw, and then you're integrating out the right-handed neutrinos, right? Then you'll be getting back the dimension 5 operator at very low energies.
Yeah, I was trying to phrase my question in terms of having somebody else do the integrating out and not telling you how they did it, but then handing you the result.
Integrating it out at scales which are far below the Planck scale. No, not integrating it out at trans-Planckian scales, right? I'm mostly concerned with what is the structure at the trans-Planckian or Planckian scales. So I think for the people at Fermilab, there's no difference in that if there is a right-handed neutrino at, let's say, 10 to the 15 or 14 GeV, that will effectively generate the Weinberg operator, irrespective of whether there is asymptotic safety with gravity or not, but in a different regime of scales.
Thanks.
Actually, I have a follow-up question. I mean, I'm just confused. Let me phrase my question naively. Do you give up on renormalizability or not?
So I would say I have it. I mean, asymptotic safety is a different concept of renormalizability, but because, what is the actual essence of renormalizability? I would say the actual essence of renormalizability is not that it's a prescription to remove counterterms, but what it actually is that it provides us with theories which have only a finite number of free parameters and which are predictive. And perturbative renormalizability automatically requires those to be the dimensionless and the positive dimension operators. Asymptotic safety generalizes that concept and says there can be theories in which you have a finite number of free parameters, but those are not one-to-one matched with these mass dimensions. And so there can be, for instance, couplings that are higher order interactions which belong to those free parameters. So I don't give up on the actual, what I would call the essence of renormalizability, which is constructing predictive theories. That's exactly what asymptotic safety does. It just does that in a different way because it doesn't use the free fixed point, it uses an interacting fixed point, and therefore different interactions can play an important physical role. Does that help?
To my understanding, your answer is no in the sense of traditional renormalizability, but you have a new way to define it, which needs to be tested.
Yeah, so I would say that the traditional notion of renormalizability is too narrow, in that if we only use that, we miss theories which are completely well-defined and predictive. And this is actually what we want for physics, right?
I have a follow-up question. In the language you use like predictive. I think you have you mean that you have a predictive approach, but do not have precise prediction to test with observations yet.
Yeah, by predictive, I mean the theory has a finite number of free parameters. Whether I can already calculate the precise values for all of the couplings which are not free parameters, that's a different and practical question, right? But in principle, it's a predictive approach.
Any quantum theory of gravity should have a finite number of free parameters in principle.
Yes,
otherwise,
completely agree with that.
Okay.
I'm just saying that if we limit our search for predictive quantum field theories of gravity to perturbative renormalizability, we might be missing physically important examples, because there's other ways of generating predictivity than demanding perturbative renormalizability. That's just one way of achieving predictivity, but that's not the only way.
Okay, we have a different question.
Kind of in the same direction, I guess. So you're looking for this non-trivial fixed point, yeah? And you mentioned that it's somewhat non-perturbative, but not too much. So the question about how do you quantify that? And also, okay, say there is some, I mean, from my QFT training, I remember there are Wilson-Fisher fixed points, and you can sort of approach them somewhat. Can you do something like this, some 1 epsilon trick if it's really close? Yeah, you see what I mean? Yeah.
Yes, yeah, thanks for the question. So first of all, how do we quantify sort of how non-perturbative the fixed point is? one way to do that is just to look at the deviation of scaling exponents from the canonical dimensions of the couplings. So if we have an exactly Gaussian fixed point, then there is no deviation between those except for the marginal directions, but let's forget about those. So the larger the deviation from the canonical scaling dimension of a coupling, the more non-perturbative the fixed point is. And so then the second question is, if the fixed point is somewhat near perturbative, is there a limit in which I can trace it back exactly to the free fixed point? And in gravity, that limit is going towards 2 dimensions, because the Newton coupling is dimensionless exactly in d = 2. And in fact, the earliest works about asymptotic safety, starting with Weinberg and then by a number of other people, exactly look at gravity in 2 plus epsilon dimensions and calculate the beta function and find asymptotic safety. And then the hope is that indeed epsilon equal to 2 is still small enough so that this fixed point is continuously connected to the free fixed point. And there are a number of studies that address that question and trace the fixed point as a function of dimensionality. They seem to indicate that you can continuously connect back to this fixed point in 2 plus epsilon dimensions, where epsilon is really small. But it's also something I would say that needs further study to sort of really conclusively establish that you can really trace it back to that fixed point.
Right, and but yes, so related to that, so you also mentioned that you check the technique you're using by comparing with, say, Ising model and conformal bootstrap. So that would be one way to verify that actually. Well, and do you have other examples? And how special is this particular example, Ising one? Yeah.
Mm-hmm. Yeah. So I mean, this method with which we look for the interacting fixed point in gravity is being applied very, very broadly. So you can apply that basically across whatever model in statistical physics you're interested in that has an interacting fixed point. And so that includes, the Ising model, but then also its extension, all of the ON models, or models with multicritical points in 3 dimensions, or various models where you have interacting fermions in 2 or in 3 dimensions. So in condensed matter and statistical physics, there's a huge list of models with interacting fixed points where people apply the functional renormalization group. And whenever there are models for which other techniques give you critical exponents, then typically if you work hard enough with the FRG, you get results that are competitive, or in some cases, for instance, if it comes to strongly interacting fermion systems, the FRG is even more powerful than some of the other methods which have difficulty with strongly coupled fermions in low dimensions. So overall, the method is extremely well established as a very good tool to study interacting fixed points. And of course, gravity is a bit special and has a bunch of sort of added complications over condensed matter models. But there's really no reason at all to doubt the method and its potential to quantitatively really precisely characterize interacting fixed points.
I have a follow-up question on this. So you mentioned in your slides that FRG approach, the Wetteridge equation, is more from the Euclidean path integral. And during this workshop and also in this week, during the Paulo Moniz talk, there are questions about, foundational questions about the Euclidean path integral. I mean, when you have gravity, especially in the gravitational context. And are these foundational questions cast a doubt on Wetteridge equation?
No, so not on the equation itself, right? I mean, of course, if the Euclidean path integral in gravity is really ill-defined, then you're deriving beta functions based on a theory that isn't really properly.
That is exactly. So there are people showing and claiming that Euclidean path integral is ill-defined. This is what some recent works by Neil Turok and some other people, I don't know the exact details. There are, I mean, almost everyone, even in the panel discussion, said that the Euclidean path integral, it is valid or not, it's an open question. So So do you accept that? If you accept it, then what would be implications for Wetterich equation?
So hang on. I think we need to sort a few things. I mean, first of all, a path integral for an interacting theory. I mean, it's very difficult to find any theory where you can really show me that this is a well-established quantity or well-defined quantity, right? The other aspect, I mean, what Neil and Jean-Luc Lehner's work and other people's work addresses is the semi-classical Euclidean path integral, and very specifically the question. If you're looking at the path integral in order to calculate sort of the wave function of the universe, or the Hartle-Hawking wave function, what are the appropriate saddle points to account for? And is the Euclidean contour that people have been choosing for decades, is that the correct contour? So, and they argue that it isn't. So that's a completely different question than using a Euclidean path integral in which you're not putting in the Einstein-Hilbert action and you're not using it to just calculate this one particular wave function at the semi-classical level, but you're using this as a general formalism in order to really non-perturbatively sum over quantum fluctuations, and you're trying to find out what is the correct action that you have to put into this path integral in order to make the setting predictive. So if the semi-classical Euclidean path integral is ill-defined or not, is a question that is completely decoupled from the question whether it makes sense to look for asymptotic safety based on a Euclidean path integral. What I will say, though, is that, of course, it's a big assumption that looking at the Euclidean path integral and trying to find asymptotic safety is really the correct thing to do to establish asymptotic safety in a Lorentzian regime. Right? Because there you're really making the assumption that this change of signature will not strongly affect the results about the existence of a fixed point. And that is, of course, a crucial question, and that needs to be addressed. And there are a number of people working on making sense out of Lorentzian functional renormalization group calculations.
Okay. Any?
I have a quick question for Lavinia. You were briefly mentioning that you get, so in this non-metricity formulation, you also get standard results for black hole thermodynamics and so on. Does the interpretation change in any ways, or is it still true in the sense that you think of microstates on the surface or at the horizon if you think about this black hole entropy, or is it something different?
Yeah, I think this calculation is completely independent of how you basically interpret that as in terms of microstates. It really, the comment that I was mentioning relies again that you can use Euclidean path integral in order to compute your partition function, right? In terms of like this, what this microstates would sum up to. But if this, so because this assumption is basically true in all this formulation, or basically because all of the formulation assume that you can do that, there's no difference in terms of that. There's only difference in the way how this action in the Euclidean path integral appears, and whether or not you need like Gibbons-Hawking boundary term or counter terms in order to observe infinities.
I see. And maybe a somewhat related question, can you formulate a generalized Wald formula then? Since in a metric formulation, you would have the variation with respect to the Riemann tensor, and now you have these extra terms. So is anything known about that?
Yes, we have a work where we basically applied Wald entropy calculation to the non-metricity case. Because in Wald case, it doesn't rely on any integral, on any path integral calculation of the entropy, but rather on the presence of diffeomorphisms. We can basically do exactly the same approach as in the standard Wald approach to general relativity. In his case, he has only the curvature, of course, but in our case, it's the non-metricity and the connection playing the role of the gauge modes or the diffs that enter in the calculation. But yeah, you can also directly apply also this approach. We have done that.
I see. Thank you.
And we have another question.
Yeah, another question for Astrid concerning the last part of your talk about the fact that WIMPs and axions seem to be disfavored by asymptotic safety. So what's favored? Have you?
Yeah, I would also like to know the answer to that question. And let me be a bit more careful with the statement, right? So I mean, it's not that all WIMPs are disfavored, right? So I was phrasing things a bit polemically. So
Right,
so I mean,
with
you know,
fixed point.
there's this
Yeah.
one particular simple case that is excluded, and the others are constrained. But if you want, you can write down a model with the dark scalar and dark fermions and dark gauge bosons, which mix with the visible fermion with the visible photon, and you can make that model work and come up with the constraints on the parameter space. It's just not a particularly compelling model, I would say, because it introduces a whole lot of new degrees of freedom in order to circumvent this original result that the portal coupling must be 0. And for the axion-like particle, I should say that we've looked at this one coupling, right, between the axion-like like particle and the photon. We've not looked at sort of proper axion models where the axion, if you're talking about something like the QCD axion, it arises from a setting where there are additional heavy fields, and the axion is a pseudo Goldstone boson of the spontaneously broken U1 symmetry and so on. So the statement about this polemic statement about no ALPs in the asymptotically safe landscape is really an extrapolation from this result that the ALP photon coupling vanishes in this very simple model. But so more work needs to be done to really investigate what WIMP models are excluded by asymptotic safety, and if you look more comprehensively on everything that you can write down with axion-like particles, is there anything that goes, or are they all excluded? So what we've done so far is really just somehow highlighting that there is a lot of predictive power in asymptotic safety, and that it makes sense to follow this approach because a lot of models can be disfavored. Now, this other part of your question, sort of, what is the favorite dark matter model in asymptotic safety? Was like sort of the natural dark matter candidate. I don't yet have a particularly good answer to that question. That's work in progress. If you ask again in a few years, hopefully I'll be able to give a better answer and tell you about the candidate for dark matter that comes out of asymptotic safety in a completely natural way.
Small asymptotic safety landscape compared to string landscape.
Hopefully, I would say. But of course, talking about the relative sizes of these landscapes is, if you want to properly do that, you need to, be able to place a metric on these landscapes in order to actually quantify that volume. And that's a question that I think will be, quite tricky. So yes.
I have a question to Lavinia. So I'm curious, as you mentioned before, that if you have non-metricity, you have more degrees of freedom. We don't see requirement of many degrees of freedom. For example, in the primordial physics, CMB heavily constrains all the multi-field inflation. So single field inflation is what seems to be most plausible thing. I would like to know your comment about that. So no role of non-metricity or any degrees of freedom for primordial physics, or you have some prediction, or it's possible to derive a prediction from these metric affine approaches?
So yeah, if you stick within standard general relativity, of course, in the connection of the non-metricity, there are no additional degrees of freedom. You still have just the 2 degrees of freedom in general relativity. So you need to consider modified gravity in order really to have additional degrees of freedom. And I was kind of just, naively trying to motivate on 1 or 2 slides that we have these challenges, right? That we have dark matter, dark energy, and we have singularities. We seem to have some observational tensions. And so naively, these are like let's say, maybe personal or subjectional motivations why I might need to consider to go beyond general relativity. And then you introduce these additional degrees of freedom. For example, if you choose f of q where you have additional degrees of freedom, and you tune your coefficients or your operators in a way that they're important for early universe, like in the inflationary epoch, then you will have implications basically coming from this inflationary epoch, right? So everything that the inflaton has impact on, then now this f of q theory will have impact on. So, or instead of having an inflaton field, the degree of freedom of f of q will be responsible to having this expansion of the universe. Or you could also say, no, I don't want to touch the early universe, but I only want to introduce that as a phenomenology for dark energy. Now you are choosing your operators or the scaling of your operators in a way that they become only relevant at late times, so small redshifts, and then you get the dark energy phenomenology. So if you say I will ignore all this question about quantum gravity, dark matter, dark energy, singularities that we encounter here and there, then we can say, okay, general relativity is the theory and it's asymptotically safe, and the asymptotically safe generates all these higher order curvature terms, but maybe you don't even need to add additional degrees of freedom. I mean, that could be one way of saying it, but we seem to see in observations that there are these things as dark energy, and it
sure.
could be even a cosmology. It might be that it's not a cosmological constant, and then you need additional new physics to explain that.
Yeah, I mean, my question is related to really observational question. How do we measure signatures of non-metricity, torsion?
I mean, in the same way as we do generically with any type of new model or new modified gravity. I mean, as I said, if you are interested in applying that to inflation, then of course you would calculate the power spectrum, for example, of your scalar perturbations with respect to your tensor perturbations. Then you would look if it has impact on your CMB fluctuations, and you would impose constraints coming from CMB on your parameters. You will look at all the maybe higher order correlation functions beyond the power spectrum. So you can do all this game that we do with our standard model. It's just now your Lagrangian has additional terms, and this will impact your observables. Or if you want to apply that for dark energy, you will have modified Friedmann equations. And then if you look now at perturbations, these perturbations will have different clustering effects already at linear order. The growth will slightly change. And then you can go and test that using various different cosmological observations.
Okay. Are there any further questions or follow-ups? So, if not, let's thank Lavinia and Astrid for the nice discussion.